Hey everyone, the topic for today is Virtual Goal Guided RRT for visual servoing of mobile robots with the field of view constraint. We've all learned how to plan a path using an RRT, but have you ever wondered how a non-holonomic constraint robot using the techniques of visual servoing would move on such a path? And keeping in mind that we want to keep the goal in the field of view. So let's look into it and let's understand how would we handle the errors that we occur through in this process. Understand about how we're about to tackle, let's look into some basic concepts. So I use the term non-holonomic. So what does it signify? First, let's see what a holonomic constraint means. Here there's an example of a pendulum that has a 2 degree of freedom in x and y, and the length here is constant. And the equation is given by x squared plus y squared minus l squared equals 0. Hence, in the equation, we can see that it only depends on the coordinates and does not explicitly depend on time. And that is what a holonomic constraint is. Now let's jump to a non-holonomic constraint. Imagine a particle trapped in a sphere. It has 3 degrees of freedom and it is governed by the equation as shown. We cannot write this as an equality, and this is what is a non-holonomic constraint. Another key difference I would say is that it is not integratable. So for example, a car, the movement of x and y cannot be integratable over time. That is why it's called a non-holonomic constraint. Now concept about let's look into the concept about visual servoing. Visual servoing is a method of controlling a robot's motion using real-time feedback from visual sensors to execute these tasks. So computer vision methods are used to extract features from the robot's operational scene and determine how the robot would move in order to articulate the image features or converge the task workpiece. For robots, the real-time pose of the robot is obtained by implementing the homography matrix decomposition method on the current and desired image of the position of the robot. Here we see the control loop. The robot uses the camera feedback to continuously track the features and move towards the goal. Understood these two important definitions, let's now move to understand the problem. The paper tackles the issue of planning a path for a non-holonomic robot that also satisfies the field of view constraint. So the first question that comes in mind, why can't we just use a simple RRT? So here we can see that traditional RRT suffers from two aspects. A non-holonomic bot cannot directly move sideways, hence when extending the path or the tree by integrating the kinematic model, the lateral error of the robot will start to occur once it approaches the goal. And as it reaches the goal, it actually increases a lot. Another issue is that since the node is randomly sampled, the final edge of the tree cannot precisely arrive at the goal node. So we'll never get to the exact goal node. So now let's understand what this algorithm brings to the table. Let's have an introduction to the algorithm. This algorithm is inspired by the approach used by robotics arm during visual servoing, but here we're going to tackle this using our mobile robot. The algorithm introduces a novel way to reduce this lateral error by using a virtual goal-guided RRT. And the main contributions include that it tackles the field of view constraint and the velocity constraint using an integrated trajectory planning and tracking control approach. It can plan the trajectory for an image with an unknown depth, and hence it can use a monocular camera instead of a stereo camera. We have a two-while robot whose kinematics can be given as follows. The pose is obtained by the computer vision methods such as the homography matrix decomposition method that is applied on the current and the goal images. Hence, the pose of the current robot frame with respect to the desired one can be estimated. Now, due to an unknown depth, we can only obtain the scale coordinates. And here we see in the equation there's a term called d star and d star here. So this is an unknown constant from the origin of the goal/desired frame to the plane where the feature points are located. And using this, we can find the kinematics in the scale space, and that's given as below. Now, understand how we ensure that the trajectory is found from the initial image to the desired image, and also remaining in the field of view of the camera. Figure below shows the approach, and we can strictly divide it into two parts. Now, let's look into those in detail. The part 1 finds a trajectory that satisfies the field of view constraints from the initial to desired pose. I keep saying this satisfies the field of view constraint, and I'll be explaining it further on. So let's just accept the fact that we are able to satisfy the field of view constraint. So the algorithm uses it to find the trajectory that is shown later on. Once the trajectory is formulated, it is then projected to the image space to ensure that the field of view constraint is met again. And only if the whole trajectory is explored, then it's passed to the second part of the algorithm. And that is as follows. Is explored, it is then passed to a closed-loop visual servoing system. This is done to ensure that the robot can track the given trajectory. The entire framework that I've shown ensures that the robot reaches to the desired pose without violating the field of view constraint. Now let's make the focus of our paper is on the part one. That's where the novelty lies. So let's look into it in detail. We'll be looking into the pseudocode to understand the detailed explanation of the trajectory planning algorithm. And later on, I'll also be explaining what does field of view constraint mean. So the code mainly contains of two stages. The left side of the image is the general searching algorithm, which is very similar to an RRT algorithm, and I'll get to that in a moment. And the right one is the greedy extension process. So now let's understand each of these processes. So the first process is in that we initialize the tree. The exploring tree is initialized with the initial pose x. Each node in this tree represents a state of the robot in the scaled Euclidean space, and it is shown as in the red box here. Now we have a generalized virtual goal. So we create a virtual goal node behind the desired pose, and this is done so as to attract the tree to grow sideways during its exploration. This means that the field of view constraint of the camera is easily satisfied. And another plus point is that the lateral error that will occur when we reach the goal due to the non-holonomic constraint would be greatly reduced. Next process is very similar to RRT. Based on the probability, we choose the random node or the goal node to grow towards, and at this if and else condition, and then we find the nearest neighbor node, and then we extend it in that direction. And this is very simple, similar to an RRT. Now, what changes is the next process, that is the greedy approach we have. After each successful extension of the tree, a greedy extension is also attempted. And here in the algorithm, the greedy is set to 0.4. So if the number generated here, this is less than the probability, then the extension is done using a polar stabilization controller. And it is given as this following in the box. Now, that's slightly complex to understand. So I'll just give you a short brief summary of what it's actually doing. In short, it basically means the controller computes the control input at each time. Hence, a very smooth trajectory is developed. And since this edge is generated using a point-to-point controller, the end error is greatly reduced when compared to an RRT. Again, the same process that the point should satisfy the field of view is checked, and the code is ended there. So now let's understand what this field of view constraint actually means. So what is this field of view constraint I keep referring to? Field of view constraint is we do not want feature points of the goal node to go out of the field of view, so that if that happens, then the robot loses track of where it is, and then we do not the robot could go haywire if the field of view if the constraints keep changing. So we can calculate this projective using the projective homography matrix that describes the mapping relationship between the desired and the current image. So here's the RNT, and using this RNT we find this homography matrix. Then we find the projective homography matrix, and now the pixel coordinates for each of these feature points. So here we have 4 feature points, right? So each of these feature points are calculated using this homography projective matrix we have calculated. And then we ensure that these conditions are met. Here the py minimum, py max, pz minimum, pz max are the constraints or the image view. So it does not go out of the image view. And also similar to the RRT, the planning process is probabilistically complete. So basically that means that if there exists a trajectory that satisfies the field of view constraint, we would find it as we increase the number of iterations. And as it approaches infinity, the probability of finding the trajectory also reaches higher. So now we have learned mostly all the concepts of it. So now let's focus on the experiments. So here the experiment setup has the following parameters, and here the distance from the origin to the plane of the feature point, D star, is 1.8 meters. So here basically these four are the feature points which I'm talking about, and this is what we're trying to ensure stays in the view of the camera. We'll be discussing mainly two experiments, so let's jump into them. So the experiment one shows the effectiveness of the approach. That's the goal of this experiment. So the first case shows an example where the lateral error is less than 0.2 meters in the Euclidean space, and that translates to around 0.36 meters in the real world. But yeah, so basically what we see here is that the red triangle is the desired pose, and these are different points that are under 0.2 meters of lateral error, and we see that the red dotted lines are the planned trajectories, and the actual visual tracking are these blue lines that we can see. And overall, since the lateral error is so less, so the planning time is really quick, and it's around 0.3 seconds. Now next is the case 2, where the initial lateral error is large, that is greater than zero point 0.2 meters. So here the the red is the desired pose, the blue is the initial pose, and we see that the robot initially goes back and then goes towards the goal. And this is done so as to maintain the feature points in the field of view. So here are the trajectories of these feature points, and each the red star indicates the desired feature point position, and the blue indicates the initial. So we see that initially the robot goes back and then goes back towards the feature point. Now let's look into the experiment 2. So basically shows the necessity of this proposed approach. So in many cases, the lateral error can be large, and the feature points could be almost at the boundary of the image. In such scenarios, any small movement could result in the feature points moving out of the field of view. So here, in our proposed approach, we see that the robot moves back twice to maintain this field of view limits, and the planning time is also high, around 1.2 seconds. The longer planning time for the larger initial error is because it needs more attempts to find the trajectory that satisfies these constraints of field of view. And the right side of the two images show the experiment using a normal visual stabilization controller. Even though we observe the paths are smoother, but we can see that the feature points go out of the field of view, and hence the visual feedback would not be there. And that is a problem because if we lose the visual feedback of the robot in the real world scenario, the system process could go haywire, and that is not advisable. Hence, we can see a proposed approach maintains these points within the field of view. Now, also, let's look at the velocity constraint. Here we can observe the velocity evolutions and pose errors, and we can see that we have a velocity saturation constraint which we want it to maintain. But since the controller cannot have this included, the actual velocities actually exceed the velocity limits in case of the visual stabilization controller. But for our normal proposed approach, we see they are well within the constraints. And this is the advantage of using the proposed approach. So by the experiments, we can now conclude that the field of view and the velocity saturation constraints can be met in the proposed approach due to the formulation and its method of solving the problem. And the VGG RRT planning algorithm achieves better end accuracy when compared to the normal RRT. And setting the virtual goal behind helps reduce this lateral error when trying to achieve the desired goal position. And we can obtain more flexible motion patterns so that the field of view constraint is satisfied for high lateral errors when compared to the normal visual servoing controller algorithms. And let's look at the references, and these are the references. So that's it. Hope that you learned something out of this presentation. Thank you and have a nice day.